Hi there, we're back to look at some of these familiar line segments and to talk about how we can determine the length of a line segment. Now, I would say that there are some, right? First of all, length of a line segment, that's the distance from one endpoint to the other, right? Line segments have endpoints. I would say that some of these are pretty obvious, right? For example, if I was to ask you, and notice the notation here, what is the length, small l, of line segment CD, notice the subscript CD, you could just count that out and say, well, that's 1, 2, 3, 4, 5, 6 units long from there to there, and we would just say, well, the length of that guy is 6 units, right? Similarly, the length of KL is, just counting down, 8 units. What's the length, though, of GH, right? And perhaps you're not too sure, I'm not, but I could make a reasonable guess that, well, I know it's at least, well, how high is it? 2, 4, 6, 7 high, and it's on an angle, so it's probably a little bit longer than that. Is it around, 7.5? Is it around 8? I don't know. I can make a guess. I know it's in that ballpark. How about, for example, line AB? How long is that? Well, it's 4 over and 3 down. I don't know, it's more than 4 because it would be 4 if it was straight across, but it's diagonal, so maybe it's maybe the length of AB is about 5. Who knows? But there's a quick way to calculate that, right? Because you know how, using rise and run, to immediately change a line segment into a right angle triangle, right? And it's pretty obvious from this that this is 3 and this is 4. And thanks to the efforts of Pythagoras, you know how to calculate the length of the hypotenuse, right? The longest side of a right angle triangle. You know that c squared equals a squared plus b squared, right? In a right angle triangle, if c is the longest side, the hypotenuse, and a and b are the two other sides, then c squared equals a squared plus b squared. And so that means for this triangle that we've created out of line segment AB, that c squared, the unknown, will equal 3 squared plus 4 squared is 9 and 16. And that equals 25. So if c squared equals 25, then mathematically the correct way to solve this is to take the square root of both sides, because the square root of c squared is c, and luckily the square root of 25 is a very easy to work with number, 5. So the length, that means the length of AB must be 5, and that means I had a pretty good guess before. Okay, so you should try and figure out what is the length of IJ using this method. So press pause and see if you can figure it out. And the correct answer is that the length of IJ is the square root of 72. Now that's an exact answer, and some of your calculators, if they're fancy, might actually tell you that it's 6 root 2. Either one is a good exact answer, right? A lot of you probably automatically gave an approximate answer. You probably punched it into your calculator and found out that the approximate answer is 8.49. In this course, we're going to make a big deal out of answers that are exact and answers that are approximate, right? This one was rounded. It's a decimal number that actually goes on forever, but we rounded it to a couple. So I'm going to be asking a lot for an exact answer, right? A root 72, right? At some point, you got the fact that c squared equals 72, and so you had to square root both sides, and that gives you that c equals the square root of 72, right? And that gives you this exact answer. You could also use your calculator to find this approximate answer. So the Pythagorean theorem works very well. Works especially if we have a picture of what we're doing. It's easy to make a triangle and see what we're doing. But I want you to be able to, just like I want you to be able to calculate midpoints without having to draw a picture, I want you to be able to calculate lengths of line segments without drawing a picture. And so we're going to actually take a minute and figure out a universal formula that will work for calculating the length of any line segment where we know the coordinates of the two endpoints. So here's the line segment. I'm going to say that I have a point P at one end and point Q at the other end. And the coordinates don't actually matter because regardless, I'm going to call them x1, y1, just like I did with the slope formula, just like I did with the midpoint formula, and the other one x2 and y2, right? And out of this, I'm going to create a nice right angle triangle, right? And this side, of course, is going to be the rise, which we know is defined as y2 minus y1. The horizontal side is going to be x2 minus x1. That's going to be the run. And so, in order to calculate the length of the line segment, we can use, again, the Pythagorean theorem, right? So if we call this C, A, and B, we know, of course, that C squared will equal A squared plus B squared. Well, what's C in this case? It's our length, so it's going to be squared. What's A? It's x squared minus x1. So x2 minus x1 squared plus the b squared, which in this case is y2 minus y1. And all we're going to do is say, well, this is great, but we need a formula that is L equals instead of L squared equals. And of course, how do we get rid of the square from L? We square root it, which means that we have to square root both sides. Right? In an equation, you always have to do the same thing to both sides. Square rooting L squared gives us L. And the rest of our formula is just x2 minus x1 squared and y2 minus y1 squared. And this here is our length of a line segment formula. So, for example, if I wanted to calculate the length of EF, well, I would call EF, or I would call E x1, y1, I would call F x2, y2. Doesn't matter which one I call x1, y1, which one I call x2, y2, just like with slope, just like with midpoint, as long as I'm consistent and the ones are together in one point and the twos are together in the other point. Here we go. Filling in x2 minus x1 squared plus y2 minus y1 squared. It's never bad to rewrite the formula. Helps you memorize it. You will have to have this memorized. So, filling in. 6 is x2. Negative 6 is x1. Watching my brackets. By the way, if you have a negative and negative, you must have brackets around that other one. And actually, it's better practice than I've been showing. Anytime you sub in, might be a good idea to have brackets around that part. y2 is negative 3. There we go. And y1 is negative 7. So I'm going to be very careful with my positives and negatives. I'm going to follow BEDMAS, of course, and say that, well, 6 minus negative, so that's a plus. 6 plus 6 is 12. That's squared. And negative 3 plus, right, minus negative is plus, negative 3 plus 7, I think is 4 squared, and so that gives me 144 plus 16, which is the square root of 160. So my exact length of EF is 160, and let's see, I know that the square, 144 is 12 squared. I know that 13 squared is 169. So this is somewhere close to 13, I think. And if I actually report what it is approximately by punching it into my calculator, let's see, the square root of 160. I get, my calculator tells me, oh, it's a smart one. It's around 12.65, rounding correctly. Okay? And again, I use the squiggly brackets to say this is approximate. I use the equal brackets to show it's exact. By the way, my calculator, because it's a fancy one, told me that this here was also 4 root 10. I would accept you reporting either one of these. So you should practice a couple. You should, as your sheet says, find the exact length and approximate length probably of line segment QR from your sheet, and the length of line segment EF. Oh wait, that's the one we already did. Maybe you should do line segment IJ instead. So figure out the length of line segment IJ and figure out the length of QR as given on your sheet. And then check back. The length of QR is exactly root 68, or if your calculator prefers, to root 17. And that's approximately 8.25 if you round correctly. And the length of IJ is exactly root 72, or perhaps 6 root 2, and approximately 8.49. All right, there you go. How to calculate the length of a line segment.